what it's all about. I think it's always the best way to start a presentation with a little quote. And Timothy Miller said on the Linux kernel mailing list 3 years ago that the goal here is to produce a graphics card which is a free software's peak dream in terms of openness. He suggested the idea that we would create a graphics card that was not just open in documentation on the register level, or open in documentation as in how it actually looks like, but more open as in recently Sun's T2 cores. Really, you can have the source of the actual graphics core. So that created a lot of interest, and from that mail, the Open Graphics project started. The Open Graphics project really has 3 phases, and we're still in the first one. The first one is really to design a development card, which has some reprogrammable hardware, and on that card we can then create a graphics core. We can test and debug and try to get it working. Then at some point, if that core works, we're supposed to make an ASIC out of it, so a real application-specific integrated circuit. And then that is something we can sell. But before we go through that one, I just want to discuss what a field programmable gate array is. First, I'm not entirely sure if everyone knows what it is. Really, an FPGA has 2 main components. The first part of this here, same part as that there, this is a lookup table. Really, it has 4 inputs and 1 output, and you can define for each combination of inputs what the output is supposed to be. So if all the inputs are 0, I want the output to be 1, and then if all but 1 input is 0, then I want the output to be something else, etc. And I can define those 16 combinations. The other part is a flip-flop, which can simply remember a byte, or a bit, sorry. There's some other logic around it, but that's not really interesting at the moment. The interesting bit is that this is a cell, really, and a Spartan 3 S4000, which is a Xilinx FPGA, has about 62,000. And this is one bit you can program. The other bit is that you can define how all these lookup tables are connected between each other. So this one's connected to another lookup table somewhere else, etc. So you're really not talking about the processor which you're programming, you're really talking about the hardware which you're programming. To give you an idea, I have a bit of Verilog here, which is the language you can program these chips in. And you can see here that I have the beginning and the end, and I say clock 1, which is a register, is now, I'm assigning clock 2 to it, and clock 2 I'm assigning clock 1 to it. If this would be a C program, what would clock 2 be? Would it change? It wouldn't, it would just stay the same because clock 2 is clock 1 and then stay the same. However, in Verilog, everything goes in parallel, so these 2 will actually swap the registers because they're done simultaneously. This is really the keystone concept of programmable hardware. You can just define parallel parts.
Yeah, in the narrative language, I mean, you have to think about it as parallel programming, or do you, I mean, there's 2 declarations that you swap them around.
I could swap them around, nothing changes. Then nothing will change. Of course, there is some sequential stuff, because you see if, and else, etc. But parts like in and end, that's just happening in parallel. And this is one module, and I can define multiple modules, which will also be working in parallel. Okay. Yeah. So I was talking about this development card. The Open Graphics Development Board 1 is this card, still in development. It has PCI-X connection, it has 2 dual-link DVI outputs, it has 200 certificates, it has a lot of features. And this is a really expensive and big FPGA, the S4000 I mentioned earlier. Right now this card is an estimated $1,500, which is kind of above the budget of any developer. And we're now working on it for 3 years and it's still available. And part of the problem with the Open Graphics project is that these 3 phases are focusing on different groups of developers. The first one is really for hardware developers to get this card working, and people who like to play with hardware are interested in a card like this. And then at some point it shifts to graphics developers who are more interested in creating a 3D pipeline and playing around with graphics. And then at the end we have this ASIC which cannot be reprogrammed anymore, and then it's really something for end consumers. So it's really hard to get everybody motivated to write something that's supposed to be for another market. So I thought in September 2007 that the font's a little small, I'm not sure if everyone can read it. I'll just read it for you. I think it's very bold to try something like this. I just think their approach to the problem could be a lot better. I had the idea that this whole concept of a graphics card which could be reprogrammed is a fun thing to do, and a lot of people would be interested in it, but this is not the way to do it. So I came up with Project PGA, which is really 2 stages. And the first one is to get the development card out for developers, and I wasn't really interested in doing it in a sort of group fashion. I just wanted to get the card working, get it out there, so that people can start working with that card. And then the graphics for with that would be an open source project where we could all work on the same thing. And that's really just for graphics developers who want to play with graphics, etc., and not spread for end consumers and everything else. So the first bit had some requirements, of course. It had to be cheap, because $1,600 would be outrageous again. So that would automatically, yeah. Sorry, could you speak on that?
Could you close the door?
Wow, then it gets really weird. One more time, please.
Sorry, is the biggest part of the cost chip?
Yeah, a big part of it is. I'm not actually sure how expensive it is, because you have to get in a contract with Linux to actually get a chip. So I don't even want to know, I think. Also because it has like 8 memory chips around it, and the PCB circuit board is 10 layer, which is again very expensive to produce, etc. And we're not talking about large phones. We can't make 1 million parts and just hope that the price goes down, because there won't be 1 million buyers. So that's a bit of a problem. So here, cheap, not high end, is really just to get smaller parts and get less features in there. Also because it was really focusing on graphics developers, not hardware developers, I wanted to make it easily reprogrammable. Usually, when you're talking about FPGAs and chips to reprogram, you're using a JTAG bus to communicate with all the chips. And for JTAG, you need a programming cable really, and these cables can run into the hundreds of euros if you really want just one cable, which is good. So, lastly, because again we're talking about graphics developers and other developers and not really hardware people, I wanted to have it fully documented, and this was really started because ATI and everything didn't actually do this, so I thought it would be a nice extra thing. Right now they are all getting started. Okay. So, the first bit was really to get a cheaper Skillings FPGA. Instead of an S4000, I'm using an S400, and instead of 62,000 cells, it only has 8,000 cells, which is still really big, but significantly smaller than the one they're using. Yeah?
Second question.
Yeah. Okay, I'll get. The really idea is that we want to have an open platform, so at some point, if you want to use a different FPGA that you can use this design, just toss out whatever you don't need and put in something new without any limitations. And you could, of course, take somebody else. Linux has a few starter kits which you could adapt, but we really wanted to get something. So, instead of a JTAG cable, I figured I'd just put a USB connector on it and make a programmer on board. So you can now just connect it through USB and reprogram the entire part without any problems. And documented, we have a website at the moment which documents every little bit. When we're talking about the graphics core, it's really still based on the Open Graphics project. They already have some parts developed, like the raster scanner, to communicate with the screen, and we just want to reuse those bits because it would be idiotic to start them all over again. And it doesn't have to be mandatory. We really wanted to also make it possible to do other things than just graphics for this part. Because really, well, I said already, several months, we also want to make a learning platform out of it. There's still not a lot of people actively involved with FPGAs and stuff, and we just wanted to make it easier for people to get started with it. So just give demonstration applications which also do other stuff than just graphics. So the layout really looks like this. Instead of PCIX, we just have PCI. Instead of the possibility to communicate with 4 screens, we just went back to 1 screen, a single VGA output. It only has 1 memory chip, which is 16 megabytes, and it only has a 2-layer PCB circuit board that's really cheap to produce. That sort of results in a card which is about to cost 150 euros, which is only a tenth of what the other card was. And the prototype is real soon now ready because we're still working on some electromagnetic inference, making sure that everything works correctly. We're still testing it because we just started in September. But progress is going really quick. I mean, we started in September, and in December we really had the circuit board itself printed already. So this is how that looked like. Then we could let a prototype reproduce, and we soldered it together on our own. And in January we had our own actual prototype. I have it here as well, but I won't be able to demonstrate it today, unfortunately. And then earlier this month we actually had the first output coming out of the card. We programmed it successfully, and this is a test screen from the dock, the digital to analog converter, just to get some output out of the card. Also, documentation is coming along very nicely. It doesn't only discuss what components are in use, but also why. So why is it an S400 and not something else? All the buses which connect all the chips are discussed and explained, so you can look up and see what each signal in each bus means. How to use and how to set up and use tools. So there's a whole tool set available to actually use the JTAG bus, and that is explained.
USB or JTAG?
Sorry?
USB or JTAG?
Sorry?
You said there are tools to that let you use the JTAG bus. But
Yeah.
there is a JTAG bus, or
Yeah, the USB is an FTDI chip, which really translates to a JTAG bus. Yes.
cool.
And not all tools were working correctly with Xilinx chips, so I wrote a small tool to actually program through USB.
Okay, using the JSU.
There's this serial engine on the FTDI chip, which I just toggled the bits right. Sorry? No, I didn't, unfortunately. I spent about a week trying to get it working, and then in a few days I programmed my own tool. So, because OCD thinks it's smart, it tries to align the bits for the proper chip. There are 3 chips in the bus. And the Xilinx tools also try to be smart, so they also align, and then of course it doesn't match up. Disabling that turned out to be quite tricky. We just skipped to that and figured I just write my own tool and get something working. The demo applications, like how to get a demo output of your screen, are still in development because we only last month got something working. But all this documentation is again very available, and it's also somewhat important because my university started sponsoring me to actually get more prototypes out, and they're also willing to buy the first batch of parts. This is just that. So, not like the Open Graphics project, that we're still not sure how many parts will sell. There will be actually a batch of parts produced real soon now, so that students at my university can start working on it. This also means, of course, that we get a lot of feedback on the documentation, as in where are the bottlenecks, what's hard to understand, and then we can work on that and improve the rest of the documentation again. So if I take another slide again, I showed you this one earlier. I can really now fill this in with this info, and you can see that my school year really consists of the first semester was to get this hardware working. The second semester would be really just to get this core working, the VGA output working. And also the first one is really, that's what I said, I could come back on this earlier, is really to get a common platform to learn how to use FPGAs and to see how graphics development will work, and to get the whole idea for the source stuff. That progression, yeah, it's also people for this. So if we would be looking at what's actually going to be inside the FPGA, I was talking about Verilog modules, which would be working in parallel with each other. This would also be a module, this would be a module, etc. And the idea is really to keep things as simple as possible. You see TBLD on the right, that's a smaller FPGA really. That contains the PCI controller, which just deals with the PCI bit of everything, and then communicates to the FPGA what needs to be displayed really, and that goes through registers to the memory. And on the other end, you have your register scanner, which is trying to output data to the screen, and that just requests from the memory manager its data and puts it out there. And if it's a text mode, it needs to translate some bit, so it has a lookup over here. In the middle, however, you see this very nice little gray box, which is your module. It's supposed to be that you can just develop whatever you want, put it in there. So I just listed a few random things. I understood that from acceleration, the biggest bottleneck was in transport layers. So that might actually not be very relevant. But some other people already suggested that there's a tool called Scale 2X, which just improves the graphics from very old games. And that would be an ideal solution to put in here, just an extra little feature. You're not really talking about driver development anymore and getting the 3D engine, for example, working on your graphics cards. You can now also define acceleration features, which would be interesting for you. So if you're building your own arcade machine with MAME, and you're using Scale 2X, you can actually implement Scale 2X in the hardware and get hardware acceleration for your arcade machine. Another discussion would be Minimec is actually implementing an Atari 500 at the moment. They're also using the same FPGA, so you can basically flash that in here, and then this whole card will turn into an Atari 500.
You wrote Amiga there.
Yeah, sorry, Amiga 500. I could look it up. I'm not entirely sure which one. I'm not looking into what else you can do. But of course, you can also do non-graphics projects, so such as cryptography, distributed computing. You can do whatever you want. It's an FPGA. If you feel like it, go right ahead. So the roadmap for this next half year would really be to get the frame buffer working, which would basically be this chunk of memory which would be constantly put out to the screen, and then the basic X driver which would get that data to the card. Now I'm not entirely familiar with X, so if somebody wants to help out, let me know. After that, we really want to go for the VGA standard, so get a VGA BIOS in there, and all the VGA options like font support, etc. So we just have, sorry?
You probably don't want that.
You won't be?
You don't want that.
Yes, well, we have to start somewhere. The Open Graphics Project is currently trying to do this, and they've been at for months.
Once you have a frame buffer, you're done. Linux will support a frame buffer.
Yeah, but the really idea is that if you plug the card in and you don't actually have any, we wanted to see the BIOS just starting.
Right, but when you want a VGA engine, this is so hard. On the decoder, it's so hard with all the overflow bits left and right. Just try to redesign and make it simple. That the registers were.
We could do that. I mean, this is all open for discussion, of course.
What if you have
sufficient to implement the text mode?
Yeah, and if you have a BIOS, it can set up your text mode. Very little software actually touches VGA hardware itself.
Set up a text mode.
Yeah, well, we just want to get something basic working, and then we can do whatever we want. Yesterday we had a discussion now about maybe implementing a 3D shader.
The thing to do, basically.
Right.
What do you need to try the thing to do? Yes, but okay, in terms of VGA, BIOS stuff, what do you need? Nothing. Nothing? Nothing. So you're done.
So really, step 3 is really just do whatever we want. Yesterday we were talking about 3D shaders, which could then support 2D on top of 3D and whatever. This is really an open-ended story. We just have to look and see what we're going to do with it. Demonstrate, I mean, this was a slide of Stefan yesterday, and you see that everything is really, they had this program, a vertex program shader, and then they changed the texture shader, and then after this was working, they changed something else, etc. It's really an incremental process, and the Open Graphics Project is really trying to jump in and start here, which turns out to be a very tricky thing to do. So with the project VGA, we're really trying to get just from the top and work incrementally and try to add stuff afterwards. Not try to have this grand design and then spend 3 years to get this grand design working.
Is the gateway actually programmable during runtime, or is it only programmable by the JTAG interface?
It's only reproducible during JTAG interface, and then on top of that you can of course create something like a microcontroller and then program it.
No, we're not talking about that, because it would be pretty cool if you put that shape and just transform it to really
Yeah, now reprogramming the chip itself here by use of JTAG takes a second.
Too long, yeah, no, that.
But it's a second. I think you just have one shader.
Which can do that, but they're probably too expensive.
Yeah, bigger FPGAs, I know they can do just parts of the FPGA and those things. I'm not sure if this one can do that.
But I think it's actually where you could add an edge other parts.
Yeah, well, we could look into it.
You need to have an edge somewhere.
So I got a few slides here to compare the Open Graphics architecture with what FPGA is doing. Open Graphics architecture is really trying to get big pipelines working immediately. Sure. And everything else like VGA support and their direct memory access and everything is controlled using a microcontroller here, which has then to communicate with all the other parts just to get things done. So if you want to write the character on the screen, I just lined out or wrote out what it has to do to actually get that working. So first of all, its data is coming in. It has to go through the XT10, then through the bridge, then through the output, then through the memory controller, and then out in there. Then the hardware controller, or the actual headquarters is called, has to actually ask from memory, I think, has anything changed, and if it has changed, it has to grab that data again. So that data has to go back all the way to the headquarters, where it then has to do its translation, I think, fallen to pixels, really. And if it's done there, it then can send it all the way back in memory, again, through all those components. And then in the end, finally, the new pixels go out to video on the right, which is really cumbersome to do. And just one note that it has here one video that includes stuff like the raster scanner, buffer, etc. So if I have this image here with raster scanner, buffer manager, and pen line, that's just one bit in the other image. So if we would be comparing here, really for Project VGA, it comes in through the PCI controller, it's sent out to memory, and then if it needs to be drawn out, it comes back from the memory, goes out through the raster scanner, and the raster scanner will do the translation here just in time. And then it goes out. So it's really a lot easier to implement. So if you compare it to, you can see that the overhead in VGA for basic VGA support is a lot less. In space, it will require a bit more space because really what Open Graphics architecture is doing is reusing all the other components just to implement VGA, and its complexity is a lot higher because of that. So VGA, the project VGA is really easier to implement. It won't implement everything from the VGA support, but the basic stuff to get on working, etc. Now I'd like to conclude my presentation here with this little snippet from the GPL license. It said that without warranty of any kind, etc., you all know the cost. If you agree with this, I could get you some hardware within a month. That's what I meant with prototype. It's real soon now. If you don't want to worry too much about stability and everything, if you want to get started with working with this card, you can get one real quick. Sorry.
Of the risk are?
Well, I am here. Risks really are, there's, for example, capacitors on it, just to get the noise out of the power supplies and everything, and those aren't fully tested yet. I know the car is working, I know it's working pretty good, but it might be that if you try to fuck it too fast that it gets unstable, and then it just won't work anymore, and then you have to reset it, and then it starts working again. So it's not really high risk or anything. But if you would be, as a regular consumer, buying one of these cars, you don't want it to crash every once in a while, so then I would get complaints. But if you just want to experiment with a car like this, then you can do it. Are there any other questions?
Are you sure?
If you want to see it up close, you can come here. Everybody's done it before.
Are the HDL compiler and tools and simulator available as free software?
Sorry?
Are the HDL compiler and the other tools available as free software?
Not all of them. There are some other projects going on to just get an open source compiler for FPGAs and everything, but they're not completely free. Right now, it's just